Okay, neural networks. So neural network, from now on, I will call it NN, sometimes neural network, is a supervised machine learning method. So it's a machine learning method first, and it's a supervised. It means that we have to use it when we have a target variable. This is our data, this is target, and this is set of predictors. And we want to associate, we want to figure out how these set of predictors are associated with the target. So we can do some predictions for this is one single observation, a new observation. What would be the outcome, the target value for this observation? And these predictors also, they are called observed values because they have been observed, right? Especially for a new observation, for a new case, these values are observed and the target is not observed. We want to predict it. The method has been around for decades and received lots of attention since 2010, especially for deep learning. And the neural networks are the cornerstone of deep learning algorithms. Basically, deep neural network algorithms are the neural networks with many hidden layers. We will talk about it. The method can be used for both regression and classification problems. So there are many reasons that I have included this method in our module. One is, well, it can handle both a regression and classification problem. Second, it is ubiquitous. It is everywhere. If you go to an interview, if you want to continue data science or machine learning paths, neural network is one of the probably the most important algorithm that you have to go through. It is the third one, so this is saying that it is universally appreciated. The third one is about, it's a cornerstone of more modern methods such as deep learning methods. And the fourth one is, it is very good at prediction. Okay, so maybe I have to keep this set of reasons here in this slide when we talk about the rationale behind neural network. Why do we need to study neural network? But in general, different methods are available because they can cope with designated problems better. So there are different problems. Different problems require or need or demand different methods. There is no one universally outperforming method that can beat every other method in every single problem. Okay, even deep neural networks that are very famous for their predictive power, they work for specifically good in very large problems, of hundreds of thousands of records or millions of records. So it is not just you can use it and you can outperform everything using a deep neural network for some problems. Even a single linear model can be a better choice than a deep neural network. So the first, this is a general thing. So for different problems, we need different methods. Neural network can outperform many methods, especially when we have very large data sets and we have enough computation power. So the computation power about these nets are important. Deep learning is based on neural network and has been amazingly successful in various fields, including image recognition, speech recognition, and etc. So the computation power is important. When you want to choose, so let me write it. When you want to choose a method, one thing that you consider, and probably the most important thing, is prediction performance. But it's not all about prediction performance. One might be about computation time, and the other one about computation power that it requires. So these two are closely related. When you have more computation power, definitely you have less computation time. So it's better to put them into one item. But still, it is important. So if you want to have a method that can be trained and can be used for prediction in a fraction of a second, probably the deep learning method or neural networks are not one of your choices, because as we are going to see very shortly, neural networks has many hyperparameters comparing to something way simpler like a decision tree. So before talking about how neural networks actually work, let's review once again that why these neural networks are important. Well, because they have a very good prediction performance, because they can deal with both regression and classification. So these two are enough for us to be motivated to study such networks. The downside is that they have too many parameters normally, and even hyperparameters. But this is not a big thing, okay? We can overcome it easily. So let's talk about how actually these machines work. Any neural network has one input layer for the predictors and one or more hidden layers and one output layers for the target. So the simplest neural network that I can imagine, let's assume that we want to formula the relation between income and years of education. So this one is the target. This one is the predictor. So we have one target, one predictor, and the data set is like this. This is the target and this is the predictor. If I want to study it, I want to model it using a neural network, I would need a one input layer, one node in the input layer. This is input layer. And this is called node. This is called node. And this is our predictor, okay, the years of education. And then this will be fed to another node. This is called hidden layer. And again, this is a node, but let's say that for sake of simplicity, we have only one single node in our hidden layer. We can have more. And then the output would be the target. Okay, which is here income. The thing is, this hidden layer also, this node has a parameter called bias, and it has a parameter called weight. So inside of it, three things are considered, and it is in this form: bias plus weight multiply to years education. But this is not equal to outcome. This is not what it gets out of the hidden layer. Actually, we use another function, let's say G. And this function is normally called, it is activation function. It can be many different things. One of them is sigmoid. One of them is tanh. One of them is ReLU. So there are different activation functions. It's not important in the scope of our course. So the only thing is we fed this linear combination of the bias, weight, and the variable into a activation function, and this output would be the output of this node in the hidden layer. Let's call it G, and G comes out, and it would be either directly the value of the target, or we can do some more transformation, but any transformation would be incorporated into G. I mean to the this activation function. Okay, so we basically receives the predictor, and this parameter, this is P1, and this parameter, this is P2. Okay, and we put them in a linear format and feed them into a nonlinear function called G, a transformation, and we get the output and pass it to the next layer. Okay, so the algorithm tries to find the parameters P1 and P2 here. These are parameters. P1 is weight and P2 is bias in our example, in a way that this G is as close as possible to the actual target values. So we have an error term, if you recall, and it is the actual value, actual target minus estimation. So this G is one estimation, and the algorithm tries to find the weight and the bias in a way that it minimizes this error. Okay, so let me clean up everything. And summarize it. So once again, let's review it. We have a target, which is income, and we have one predictor. A neural network is composed of three components or set of components: the output layer, the hidden layer, and we might have more than one hidden layer, and the input layer. In the input layer, we use the predictor, and we feed this predictor value into the hidden layer, into one of the nodes or any number of nodes that are available in the hidden layer. We will see a general form, and we use two parameters. So it's not only the predictor, it's a weight multiply to this predictor and a bias value, a constant value at the start. So this is a linear combination. Inside this hidden layer, this linear combination is fed into a nonlinear function. Okay? And if you call this value as star, star would be the output of this specific node and would be fed into the next node. Here we have one node at the end, which is the output layer. So the predictor value is a known value. It is an observed value. We don't know what would be the weight and what would be the bias. This is a parameter, and this is a parameter. Like, it doesn't matter whether parameter 1 or 2 from the left side or right side. So the neural network tries to find this parameter and this parameter. So let's write it. In order to minimize error. And you know the definition of error. Error is the difference between the actual minus predicted. So how does it do so is, I'm not going to explain it. It's beyond the scope of our module. It's enough to know the level that you know now. And this is a general form. So we can see that input layer, hidden layer, and output layer. So instead of one node in the input layer, we have now P node, 1, 2, 3, like this is I and this is P. We have P predictors. Here we have, let's say, 1, 2, and K nodes in the hidden layer. And at the end, there is an output layer. So the predictor x1 with the value of the weight corresponding to the first node and the weight and the bias would shape a linear term. It is b1 plus weight 1 multiplied to x1. It is here, this sigma is exactly the term that I showed. And then we use a function. This is the g function that I explained. Here it is said a in the name of activation function. And the output would be one of these new weights. Sorry, the output would be, and the output would be one value that is fed to the next node. So it might be very confusing for you. I do not insist on learning the nuts and bolts of neural networks. I just wanted to give you some sense that how a neural network works. And if you get some intuition that how this system works, then it's enough for the scope of our module. And this is the output layer. Normally output layer, they have one activation function for themselves, like any other node. So every node except for the hidden layer, they have one activation function. And then at the end, we get the predicted value. So the goal of the algorithm is to figure out these weights and biases, these parameters, in a way to minimize the error. Okay, the last slide about neural networks. When to use them? Well, they work for both regression and classification problems. So you can use it in every sort of problem. Neural networks should always be one of the tools that you use because they are amazing in prediction power. The downside is, okay, the questions like how many layers, how many hidden layers, how many nodes in each hidden layer. So this is one question, this is two questions. What are the activation functions? And at least these are the parameters. There are more parameters actually, that these are hyperparameters. These are the parameters that the method cannot set up itself. So you have to set it up. And there is no straightforward answer to tell you that how many hidden layer, how many nodes in each hidden layer. And you know the number of combinations that you can have is unlimited actually. Okay, and again, how to figure out the hyperparameters using trial and error. A process called hyperparameter tuning. Okay, it's basically trial and error. We change these knobs in order to get the best prediction, the lowest error. But anyway, when we have more and more hyperparameters, our problem to find the sweet spot, the sweet combination of these hyperparameters would be more time consuming, would require higher computation power and computation cost in general. And that's it about neural networks. We will talk about another algorithm in the next part.